This question takes us through both bonding and amount of substance topics. It also includes a 6 marker to begin. So we're going to take a look, try each section of it first, A through to D, and then review your answers. So here's A, B, C, and finally D. Okay, so let's start reviewing our answer. We are told here that sodium bromide has a higher melting point than sodium, and that sodium bromide also has a higher melting point than sodium iodide. And we've got to reason that out and explain why that is the case. Now, as always with a 6 marker, there are 3 different levels that you are aiming for. For level 3, you need all 3 stages covered and the explanation virtually complete. Level 2, you need 2 stages covered or 3 stages attempted. Level 1, you need 1 stage completed or 2 stages attempted. Now, when we actually break down what the 3 stages are here, the first one is the consideration of sodium. Sodium, we need to identify what bonding is present, and it's metallic bonding. And metallic bonding is where we have strong electrostatic forces between positive ions and delocalized electrons. We do need to get that key terminology into 6 markers. So we would say delocalized rather than free. And it's a giant lattice structure. So I've now completed one of the 3 stages. I've actually got to 2 marks before I write anything else. Now, when we then consider NABR and NAI, they are both ionic bonding. That's electrostatic forces between oppositely charged ions. And they also both have a giant lattice structure. So we have got 2/3 of the way through this. We have explained in great detail how sodium bromide, and sodium iodide exist, how they are bonded together. But the question is all about the comparison. And if I look, I can say that ionic bonds are stronger than metallic bonds. Now, I may not have known that, but I know it's the case because sodium bromide's melting point is higher than sodium. That means that there's a stronger electrostatic force, moving on actually, stronger electrostatic attraction between oppositely charged ions in NABR than there is in NAI. And again, we know that because NABR has a higher melting point than NAI. The one extra bit of knowledge that you would need to add in here is that that's because the bromide ions are smaller than the iodide ions. So if you've covered all 3 of those stages to a good standard, you're moving into level 3 and getting 5 or 6 marks. Moving on to B. And we have an ideal gas equation. I'm still going to recommend on any ideal gas equation, and you'll see this on every video where there is a question, that you're going to start by listing PV, nRT and putting in all of the figures that you either know you're calculating or that you have been given. And you can see here I've taken directly from the data R, P and T, and I know that I'm calculating V, so I've put a little x there. By going through systematically, I can now go through and check which I need to change because the units are wrong. And you can see that pressure needs to be converted to pascals and temperature needs to be converted to Kelvin. Now we need to do some work to get N. And so we're going to need the equation here. And the equation for sodium with water is one of the standards that could come up relatively often. It commonly comes up as GCSE questions, but will continue to do so at A level. And you can see that 2Na and 2H2O make 2NaOH and H2. Now, where do we go from there? I've got 250 milligrams of sodium at the start. And it's milligrams, so I need to convert it to grams if I'm going to work out the number of moles. So I take my 250 and divide by 1,000, and then I multiply that by 23, divide that by 23, and I see that I've got 0.0109 moles of Na. Now, it's not the Na that I'm interested in really, because the ideal gas equation is only interested in gases, and the gas that we're making here is hydrogen. So I need to know how many moles of hydrogen I'm going to make. Well, the mole ratio is 2 to 1, so I'm going to halve that figure. And I see that for moles of H2, I have 0.00545. So I can put that into my PV-nRT list, and I'm now ready to do the ideal gas equation calculation. I'm going to make V the subject. I'm then going to substitute the figures in, and I'm going to get to a volume of 1.33 by 10 to the minus 4. However, we know that the ideal gas equation calculation calculates volume in meters cubed. So to convert that, I'm going to need to multiply that by 10 to the 6 or a million, and I get 133 centimeters cubed. Moving on to part C, calculate the concentration in moles per decimeter cubed of sodium ions in the solution produced in the reaction. Quite a straightforward question after everything we've just gone through. We know that we had 0.0109 moles. We calculated that as part of our previous calculation, and we know the volume was 500 cm cubed, which I'm dividing by 1,000 to convert to dm cubed, and I get to a concentration of 0.0217 mole dm to the minus 3. Final section, we are on the shapes of molecules component of the bonding topic, and we're told that we're dealing with NH2-. Well, let's build it up with a dot cross diagram first. My NH bond will be a pair of electrons, one from the N, one from the H. Nitrogen is in group 5, so it has 3 more electrons around it that are unpaired. But this is NH2-. That minus means an extra electron. So I add that on, and what I can see is that I have 2 bonding pairs and 2 lone pairs, which takes me to 4 electron pairs in total around my nitrogen. Now, 4 electron pairs tells me it's based on tetrahedral. So my structure for the first mark will be the tetrahedral structure, but 2 of the bonds replaced with lone pairs. Please always remember to include that cloud with the lone pair of electrons. Now, it's not finished yet. I've not got the mark because this is negatively charged, so I need to reflect that with a negative and square brackets. In terms of the bond angle, you have to know that tetrahedral have a bond angle of 109.5 and that each lone pair will reduce it by somewhere in the region of 2.5 degrees. So for that reason, the bond angle is 104.5. The justification for my prediction, or your prediction, first of all, is an awareness that the electron pairs will repel to be as far apart as they can possibly be. And the second justification mark is for then recognising that lone pairs are more repulsive than bonding pairs. So the lone pairs actually push the bonding pairs slightly closer together.